Donc, il n'y a plus qu'à voir si ça fonctionne. Vous êtes en direct. Super. Ouais. Ouais. Je vais couper pour l'instant là. Je vais regarder sur mon portable la vidéo YouTube. Alors, en attendant, je vais faire un monologue. Bonjour, je m'appelle Kévin. Mon nom de famille, c'est Colin. Comment allez-vous? Je sais, c'est fait exprès. Alors, attends, la vidéo YouTube, elle est là. Je vais faire un monologue. Bonjour, je m'appelle Kévin. Mon nom de famille, c'est Colin. Comment allez-vous? C'est bon, ça marche. Essaye de parler, Fabricio. Ah bah non. Ok, c'est cool. Ouais, jusqu'au moment où j'ai de sortir la blague et il y a un membre du jury. Ouais, voilà. Je sens bien que le truc va arriver. On va éviter. Je vais me chercher un verre d'eau. Hop. Elles sont vraiment pas confortables, cette chaise. Je suis obligé de mettre un oreiller et aussi un rehausseur pour que je sois à la bonne hauteur. Il faut pas que j'oublie que la caméra est là. De toute manière, je peux. Ouais, bon, après, si ça arrive, tant pis. Si on n'arrive pas à la faire redémarrer, tant pis. Hein. On réessayera au niveau des questions. Un petit truc, oui, parce que là, sûrement, les gens sont en train de se connecter. Ils pensent que je parle tout seul, mais il y a quelqu'un d'autre actuellement. Et je ne parle pas tout seul. Juste un truc, ouais, il faut. Oui, mais toi, on t'entend pas. Et ouais, mais actuellement, là, on est 4 maintenant spectateurs sur YouTube. Donc, il ne doit pas y avoir 5. Et ouais. Et donc, ouais, Fabricio, du coup, un truc, quand les membres du jury vont se connecter, tu vas voir, tu vas laguer. Donc, pas de panique. Moi, je commence déjà à laguer, là, en plus. Non, c'est bon. J'ai la tablette, là, pour écrire pour les questions. Mon Dieu, c'est horrible. Oh, ça va être une horreur. J'arrive pas à écrire dessus. Ah si, ça fonctionne, ah, ça marche bien, mais c'est juste moi qui ai une écriture pourrie, en fait. J'espère que je n'aurai pas utilisé la tablette. Oui, oui, elle est là. On la voit d'ailleurs sur le. Si. Non, on la voit pas sur YouTube. Ah, si, si, c'est bon, on la voit, mais c'est bon, on la voit. Ouais, ouais. Ah oui, mais je sais pas. Peut-être qu'il y a l'option sur Zoom, hein. Non. Ouais, non. Bon, tant pis. Là, c'est bizarre parce que comme j'ai les écouteurs, je m'entends pas trop parler anglais. Donc, j'imagine pas à quel point ça va être horrible. Ah, on entend un peu, en fait, je crois, au ventilateur. C'est bon. Bah, dis donc, t'as pas fait les cours de TC3? Oui, non. C'est DCA ou ACD. Non, ah, DAC. DAC, c'est ça. DAC ou AD. ADC. Ça, c'est drôle. Bon, il se connecte dans 9 minutes, normalement, le jeu. Tu vois, toi, le nombre de spectateurs simultanés? Ouais, c'est ça, ouais, je vois pareil. Putain, il y en a 7. Ah ouais? Alors qu'ils ont même pas vu sur quoi ils vont tomber, les pauvres. Je dois t'avouer que là, le stress, il monte un peu quand même. Ah. Le chat YouTube et oui, bah, ça je sais, je l'ai interdit. Oui, j'ai interdit le chat YouTube, hein, pour ceux qui voudraient mettre des choses, étant donné que je ne peux pas gérer ensuite en même temps la présentation et les chats. Et oui, Eva, c'est normal que tu ne m'entendes que moi et pas Fabricio, donc je ne parle pas tout ça depuis tout à l'heure, hein, je suis encore mentalement stable. Parce que en fait, Fabricio a supprimé son microphone. Donc, le seul audio qui ressort de l'ordinateur de Fabricio, bah, c'est ce qu'il entend actuellement. Ouais, mais ça, tu fais pas. Parce que là, il vient. fait, il peut aussi hijacker ma présentation en mettant tout ce qu'il veut. Donc oui, Rory peut mettre aussi du Francky Vincent pour m'embêter pendant ma présentation. Et le pire, c'est que je ne le saurais même pas. Parce que je ne suis pas sur YouTube en ce moment. Heureuse d'apprendre que Kévin est mentalement stable. Oui. Je commence à m'inquiéter, moi. Elle s'inquiète pourquoi? Elle est en train de me faire stresser, en fait. Ah. Bonjour à tous ceux qui sont déjà là. Merci d'être venus à ma présentation. Si jamais il y en a. Ah bah non, qui voulait t'envoyer un message. Ah, bah ma mère qui voulait m'envoyer un message. Bah désolé maman, un message privé pour ma mère. Puisque, ouais, bah apparemment. Et oui, non, c'est juste que si je laisse le chat live, je vais avoir, ça il faut que je le coupe, je vais avoir des gros problèmes. Il va y avoir des bots qui vont venir se rajouter au chat live et qui vont mettre n'importe quoi. Donc, je suis obligé de supprimer le chat. Non, c'est en public, en fait. Je me suis dit, si jamais quelqu'un tombe accidentellement sur la vidéo et aimerait écouter quelque chose sur l'informativité des données, même si je doute quand même que ce soit le cas, eh ben, ils peuvent. Ah, bonjour Marion. Bonjour Marion.
Bonjour Kevin.
Ah, c'est bon.
Voilà, c'est bon. J'avais pas branché encore mon micro. Tu m'entends bien ou pas?
Oui, je t'entends très bien de mon côté.
D'accord.
C'est pareil?
Impeccable. Oui, super. Pas de problème.
Très bien.
Voilà, normalement, je vais passer du coup sur la... Ah, tu me vois pas peut-être? Si?
Si.
Tu me vois ou pas? Ah,
ouais,
si?
ouais,
Ah, d'accord. Ok, très bien. Ok, donc moi... Ah oui, moi, je te vois toi et l'écran, donc c'est bien.
Ok, très bien. Et il y a aussi, donc là actuellement sur le Zoom, il y a aussi un de mes collègues qui est en train de faire le live stream.
Oui.
Parce que j'ai décidé de faire le live stream sur un autre ordinateur pour éviter d'avoir un problème.
Ouais, bah, c'est bien.
C'est Fabricio Sagi.
Bonjour Fabricio. Oui.
Ouais.
Ouais, c'est une très bonne idée parce que effectivement, ça peut surcharger ton ordinateur et t'embêter pendant la soutenance. Ouais,
et c'est effectivement le cas.
Ouais.
Donc,
et en plus, comme il fait un peu chaud, enfin, je sais pas quelle température il fait sur Lyon, mais comme il fait un peu chaud, les ordinateurs ont déjà tendance à chauffer par eux-mêmes.
Ouais, et oui, on a combien aujourd'hui, Fabricio? Nous, 32, 31, je sais plus. Ouais. Et bon, moi, j'ai mon ventilateur à côté qui est en train de souffler sur l'ordinateur, si jamais. Donc, voilà.
Ah, d'accord.
Ça ne pas exploser pendant la présentation.
D'accord.
Hello, Johan.
Ah oui, tu vois que... Ah, ben, j'ai perdu tout le monde.
Johan, can you hear me?
I hear you loud and
Okay.
clear.
Yes. I don't hear you very well. Your sound is very low. I don't know if it's me or maybe I'll increase the sound. Can you try to speak again, please?
Yeah. Can you hear me better now?
Yeah, it's better. Thank you.
Yes. Perfect. Hello, Johan. How are you?
I'm fine. And what about you?
Nice. Thanks. It's nice to see you again.
Yes, it's not
to see you. Yes, with the virtual connection, but anyway, it's better than nothing.
Yes. When we were asked to come to Lyon some time ago, it was a nice prospect, but now things changed.
I fully agree with you.
And currently it's quite hot today in Lyon, so it's not very good.
Yeah, no, here it's sunny, but not so hot.
Oh, yeah.
Okay. Kevin, just a question because I don't see myself from this. So I don't know because at the point it's the system is asking me if I want to change the camera, but since I don't know if the camera is seeing me or behind?
No, I see you. We see you.
Okay.
I see you, and on the YouTube live stream, we see you also. There's no problem.
Okay, so perfect. So basically, the idea will be maybe to remove the camera during the
Yeah.
I mean, during your talk at least, just to be sure that we will not be too. Well, I don't know. Maybe it could be too heavy to get all of the camera.
I think so. Yes.
I'm checking. Where can we switch off the camera? Stop.
Well, for now it's okay. I think it's just when we will start. I think now it's okay.
Yeah, but I like to try it now because I'm not used to Zoom.
Yeah. Oh, yeah. Okay. It's the same for me.
Hello, Xavier and Laurent.
Okay.
Hello. Hello, everybody.
Bonjour, Xavier. Bonjour, Laurent.
Hello. Bonjour à tous. Good afternoon, everybody.
Hello.
Good afternoon.
Okay, just to try, Kevin, can you just for one moment remove your slide? Not remove, but if you don't share your screen, I mean, what can be seen?
Stop it.
Okay. Okay, so it's quite bizarre because I see nothing now. Okay. Oh, never mind. Then. Okay, well, you can switch on again your screen. Yeah.
Okay. Up. No, which one? This one. Up.
Okay, perfect. So to be sure that I well understood, so your Ph.D. So in the Zoom into the Zoom connection, we will be only the committee members and Fabrizio.
Yeah, Fabrizio is hosting.
Okay, and so the let's say the public, the others, will join the Ph.D. only as a YouTube link or something like that. Okay.
Yeah, it's like
okay. So they can hear what is going on.
Normally, yes.
Yes.
They cannot interact with us.
Okay, they cannot interact. Okay.
The presentation.
Okay, but they can have access to your presentation, so it's good because for generally a Ph.D. is open, so it's definitely a good idea to have this YouTube link.
Yeah, and I would want you to have some public because after 3 years, I wanted a little.
I agree with you. Yeah. Sorry. Up. Shoot.
Okay, so
I can imagine that it's not so nice to have a presentation like this today for you after 3 years.
Yeah, yeah, but well, we do not have a choice, and so
but anyway, it will work. You will see. No worries about that.
Yeah, normally it will. It will.
Yeah.
I believe.
I'm sure.
So yes. So what did I want you to? Nothing. I think. Yeah, I have also the possibility to write on, to share a whiteboard and to write something, but I just need to warn you. I have a really bad handwriting with this. So, yeah. I apologize in advance for this.
Okay, I can understand. But if you need this, for sure you will not have to write big things, but just maybe to help you doing some explanation.
Well, Anton has joined the meeting via the YouTube because Anton and Gerard were also involved in this project, but unfortunately, for this thing, they will only look via the YouTube streaming.
Okay, but do you want to invite them to be part of this Zoom Teams? Zoom team?
Yeah, well, it's possible. Gerard will look at tonight, I think, because he's in
Okay.
at a COVID meeting at the École Centrale. But
okay, it makes sense.
He's looking on Zoom, so on YouTube. So
okay.
Yeah, well, we could send him the link also. I guess he's hearing us. So.
Okay. Yes, it's a real pity to have this kind of PhD via virtual links and not a real face-to-face presentation. But anyway, we have to do like this sometimes.
Hello, Guillaume.
Hello, everyone.
Salut, Guillaume.
Can you hear me?
Yes.
Yep.
Perfect.
Hello, Guillaume.
Hello, hello.
Fabricio, do you have a problem for now for the live stream, or is it okay? Okay, thank you.
So who is missing?
Hokan?
Okay, I see Hokan. Nice picture.
Yeah, for the moment you see KTH, you don't see Okan.
Yes. KTH is arriving. Kévin is here. Okay.
Hello, Hokan. Can you hear us? I think not, or maybe it's the contrary.
No,
It's
see
quite,
Hokan.
it's quite bizarre because neither his micro nor his camera is getting green. So maybe we have no connection.
On my side, I see him move, but any noise, any talking. Hokan?
Hello.
Hello.
Hokan is coming.
Ah.
Are you here? Okay.
Hello, everyone.
Okay.
Hello.
Hello, Hokan. Can you hear us?
Yes.
Okay, perfect.
Okay, great.
So it seems that we are all present.
Yeah.
Kévin, you are here. It's better. Guillaume, Johan, Hokan, Laurent, Xavier. Yes. Okay. And concerning the YouTube link, it will be open at 2, or is it already open?
It's already open. I have 16
okay.
people already on the link.
Okay, so maybe we can just wait for 2 o'clock.
Yeah.
If you give this information to the other, I think maybe it will be easier to wait for this.
Okay. I agree with that. So yeah, for other members that are just connected, there is one of my colleagues, Fabricio Sagin, who is doing the live stream on his computer in order to avoid me to have some problem during the presentation.
Good idea.
Fabricio Sagin, who is currently in the Zoom meeting.
Hello.
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 Okan, how do you explain the light on your chin?
Sorry.
When I see you on the image, I see
Yes.
some light under your chin.
That's the sun.
Okay.
I don't know. You have heard about it.
No, but it's strange.
I don't have any curtains to cover the window with, and so
Okay.
it's a bit hard to move the table. So I
No,
tried.
no, that's fine. But just
yeah.
to get an explanation, because it's strange to have light under your face. So I was wondering where it comes from. Okay.
Kevin, yesterday, well, not yesterday, but Tuesday, you said that it will be maybe better to give me the animator role. I mean, for this team session, just to be sure.
I will give you after the presentation, because I think
perfect.
My slides, if you are.
Okay, it's okay for me. Just to know how it will work when the presentation will be finished. Presentation, the question one will be finished. Then you have to move and come back again. Okay.
Okay. Xavier, I'm going to send you the slides. I know that you asked me this. And
the other remark is it will be the same during the committee meeting. It will be interesting to cut the connection with the YouTube link for sure.
Yeah, of course. I can stop it from here, and then I will ask Fabrice to cut the connection.
Okay, perfect.
Okay, just no. Okay, what can't I open? I need just to wait. I will stop sharing my just for a moment. Okay. And okay, Xavier, I just sent you the slides.
Okay.
So I can go back to sharing. Okay. No.
Okay. Are you okay, Kevin? Are you ready?
On my side, I'm ready. Fabricio, is it okay for the live stream? We can start. Okay, great.
Okay, perfect.
Okay, so just
good.
So if it's okay, then I will start then.
Okay, so it sounds good. So well, welcome everybody. So if I well understood, we even if we cannot see all of you, we are quite a lot behind our screen to hear Kevin presenting his results. And so this difference will be for sure a little bit different from what we are used to know, since it will be given by virtual connections. So, but what is quite nice, I think, is that not only the committee members can follow you, but also your friends and other people from thanks to a YouTube connection. So, well, it's my pleasure today to chair this committee for this virtual but very real PhD defense. So let me first introduce the member of this committee. So starting with the reviewers. So let's start with Johan Schaukens. Sorry for the presentation, for the pronunciation, who is professor at Universiteit in Brussels in Belgium. Guillaume Mercer, who is associate professor at Université de Poitiers. They have together already given a huge work on your thesis since they provided a review on it. Then today we also have the chance to welcome Håkan Hjalmarsson from KTH Stockholm in Sweden. And Xavier Bombois and Laurent Bacot are your co-promoters. And last, myself, Marion Gilson, I'm a professor at University of Lorraine. So, well, we are here today to listen to you. So I can imagine, Kevin, that it is not exactly the way you have, the way you are presenting your result today is not exactly what you are expecting during your 3 years. But anyway, we are here for you, and the job will be done in the same manner. So you will have approximately 40-45 minutes to present your work, and then the committee member will have the opportunity to open the discussions and so on. Okay? So
okay.
The floor is yours.
Okay, thank you. So before starting, I want to thank everyone here for attending my PhD defense. So the jury on Zoom and people who are following it on YouTube. So here in this presentation, I will give a brief summary of the work that I've done during 3 years for my PhD thesis. And in order to do this, we are going to divide this presentation into 4 parts. So first, I will give the context of the PhD thesis. Then we will switch to the theoretical work on the data informativity analysis. Afterward, I will present to you the practical work on the identification of the MEMS gyroscope. And finally, I will give a conclusion and some perspective for future works. Okay, so let's start then with the context of the PhD thesis. So some first technical details about it. So it's a PhD thesis that has been funded by BPI France, which is basically a French public investment bank, through the Next for MEMS project. It lasted less than 3 years, and my supervisors are Xavier Bombois and Laurent Bacot. So now let us focus more on the research context of the PhD thesis. And I will start with an observation, is that in every engineering field, we need to model the dynamics of systems for different purposes, such as control synthesis, prediction, health monitoring, and so on. And if you want, for instance, great control performances, you need to design this controller based on an accurate model of the dynamics of your system. So this presentation will be about getting accurate model. And there might not be a best way to obtain this accurate model than to use system identification, which is basically the modeling of the system with experimental data. And if you want, system identification is like a cooking recipe. It has 3 different ingredients. The first ingredient is a model structure. So it's basically a set of candidate models for our system. And we are going to assume that there is one model that can model all the dynamics of our system. And often this model is called the true system in the literature. In order to estimate this true system, we are going to consider a second ingredient, which are the experimental data. So here we are going to consider input, output data collected on the system. And the last ingredient is an identification criterion whose purpose is to rank the model on the ability to fit on the experimental data. And of course, the last thing that we will obtain after this cooking recipe is what we want, of course, is the true system here. So you can meet several cases in system identification depending on the properties of your system. So your system can be single input, single output SISO, or it can be multiple inputs, multiple outputs MIMO. It can be linear or non-linear. It can be in open loop or in closed loop, or even worse, in a network, and so on. So you have multiple cases. And you have also a lot of methods in system identification that have been developed. And here in this presentation, I will only focus on the prediction error method. Okay, so the first question that I want to ask here in this presentation is the following one. Does any data set guarantee an accurate identification? Well, the answer is quite simple. No, it's not the case, because your data set must guarantee one fundamental property, and it's called the data informativity, which is basically the property that we are going to focus on here. So basically, the data informativity is linked to the quantity of information about your system that are carried by your data. And this quantity of information depends on the richness of your excitation. And if I can illustrate what basically is data informativity, so it's a sine qua non condition. You have it or you don't have it. There is no in-between case. In the case where you don't have the data informativity, it means that your excitation is not in our reach. And in this case, several models explain perfectly your data. And this is a problem because we know that there is only one model that can explain perfectly the dynamics of our system. But in this case, we can't discriminate this model from the other non-accurate model. And when the excitation is in our fridge, in this case, you have the data informativity, and here you have a proper ranking, and the model that you will normally identify is this one. But it's not really true, because the information in your data will be always corrupted by some noise. There is always noise everywhere when you do some identification. And so basically, the identified model that you will obtain when you have the data informativity is the true system plus some uncertainties. But the nice thing with the data informativity property is that it implies a second property, which is the consistency. And basically, the consistency is the fact that the uncertainties will decrease when the number of the number of data increases. And so another way to say it is that your model will get more and more accurate when the number of data increases, since it will converge to the true system. So that is why data informativity is a really important property. And so this property has been widely studied in the literature. So mostly for linear systems identified in open loop or in closed loop. And here I give two results that we have in this case. So it's necessary and sufficient condition. So if you consider, for instance, a SISO finite impulse response system that you identified within a SISO finite impulse response model structure in open loop, then you will have the data informativity if only if the number of non-zero amplitude frequency in the power spectrum of the input is greater than or equal to the number of parameters of your model structure. If you apply this result to the multi-sign case, you will have the data informativity if only if the number of sinusoids is greater than or equal to the half of the number of parameters. Okay, so here we have nothing more to say in the SISO case because everything has been done. We have necessary and sufficient condition. Let's move to the MIMO case. And here things are really different because if you look for results for the open loop and the closed loop identification case with an external excitation, there is only one condition. And this condition is based on the positive definiteness of the power spectrum of the excitation at all frequencies. So you can see that this result is inspired from the one of the SISO case. However, in the MIMO case, we have the problem is that this result is too restrictive. For instance, if you consider multi-sign excitation, this property will never be satisfied. So this is a problem because it means that for multi-sign excitation and for MIMO linear system, we do not have a result to verify the data informativity with multi-sign excitation. So it's a problem. And so that is why in this PhD thesis, we have decided to develop new conditions for the data informativity for linear MIMO systems identified in open loop and in closed loop. And in the thesis, we have developed these results for MIMO classical model structures such as ARIX, Armax, Bot-Jenkins, output error, finite impulse response, with multi-sign and filtered white noise excitation. However, here in this presentation, I will only focus on a particular case, which is the open loop identification of MISO finite impulse response model structure with a multi-sign excitation. So really to keep things simple, but it's not so simple because we will see that it will give a big picture of the result that we have here for the other model structure. Okay, so since the beginning of the presentation, I only focused on linear systems. But we know that most of real-life systems have nonlinear dynamics, such as the MEMS gyroscope, which is basically the real-life system considered in this PhD thesis and in the next 4 months project. And we will see that the dynamics of the MEMS gyroscope can be modeled with several models of this form here, where U is the input, Y the output. And here you can see that indeed we have a nonlinearity. And here we have 3 transfer functions that we want to estimate accurately, of course. And the nice thing with this kind of nonlinear system is that it can be accurately identified with the prediction error framework. So that's nice. However, if you want to get an accurate modeling, you need to provide here again the data informativity. And so that is why we are going to study the data informativity for this kind of nonlinear system. So it is the 3rd type of contribution of this PhD thesis. And we will do it for any integer n. And then we will see that we can apply this result for the identification of a MEMS gyroscope. And this problem, we will see it later. Because what we are going to do now that we are going to do a presentation of the theoretical work on the data informativity. So I need to warn you, things are going to be more technical. So another way to say it is that now mathematics are coming. Okay, so let's start with a linear case. And so here we are going to consider a discrete time MISO system with P inputs given by this equation here, where Y is the output, U bold is the input vector, E a white noise, and G0 is a row vector of P transfer function. And we want to estimate with an identification this transfer function. So we are going to consider first a MISO FIR model structure given by this, where theta is the parameter vector, and G bold is a row vector of P independently parameterized FIR filters given by this, all parameterized by their own parameter vector theta k. And basically, theta is the concatenation of all parameters vector theta k. So we are going to do a simplification. Again, here we are going to consider that all FIR filters has the same delay equal to 1 and the same degree equal to m, meaning that in theta k, I have m parameters to be identified. So since we have P transfer function like this, I have in total P times m parameters to be identified in theta. And we are going to consider a classical assumption that is made in system identification, and it's the full order assumption. So it means that our model structure can capture all the dynamics of our system. Mathematically, this corresponds to the fact that it exists a true parameter vector theta 0, such that this property holds here. And our goal then is to find an accurate estimate of theta 0 by using experimental data. And since we need experimental data, we need to excite our system. And here we are going to consider multi-sign excitation. So consider that you have S different frequencies, so omega 1 until omega S. Then each entry UK of U ball can be rewritten as a linear combination of sinusoids excited at these frequencies here. And here lambda KL is an amplitude and psi KL is a phase shift. Okay, so by doing this excitation, we collect a set of n input-output data. Then we build what we call the predictor, which for MISO FIR model structure is simply this signal here. And finally, we can build our estimator for theta 0, denoted theta at n, which minimizes a least square criterion on the prediction error given by this. Okay, so that's basic stuff. And here what we want theta at n to be an accurate estimate of theta 0. And for this purpose, as I said at the beginning of the presentation, the data must be informative. And here I give the definition of the data informativity for finite impulse response model structure. So basically, you will have the data informativity if for all parameter vectors theta prime, theta second, this property holds here, where here the operator E bar is the well-known operator defined for quasi-stationary signal X. Okay, so that's quite mathematical for a definition. But basically, this definition means that two different parameter vectors generate two different predictors. Another way to say it is that there is a bijective mapping between the set of parameter vectors and the set of predictors. So it's as simple as this. And here, as I said at the beginning of the presentation, if you consider multi-sign excitation and MIMO model structure, or here MISO FIR model structure, we have a problem is that there is no result for the data informativity in this case. So we are going to develop a new result. And for this purpose, let's start from the definition of data informativity. And what we are going to do is that we are going to rewrite the term here. Because if you remember, G bold is a row vector of P transfer function. So this can be rewritten into this form. Now, each GK is an FIR filter with a delay equal to 1 and a degree equal to m. So by doing the filtering between the FIR filters here and the signal here, I can rewrite this into this form. And so here I have a signal vector that is called a regressor. Now, since this is true for all k from 1 to p, then I can rewrite this into this form. Okay, and here again, we have what we call a regressor. So now if I inject this expression into this equation, I can rewrite this property equivalently into this one here. And so I will have the data informativity if only if this property here is satisfied. And here it's quite easy to conclude because you need this matrix here to be positive definite. And so this is our new result, that we will have the data informativity if and only if the regressor phi defined here is such that this matrix here is positive definite. And a regressor phi such that this matrix here is positive definite is said to be persistently exciting. The nice thing with this result here is that if you apply it to the SISO case, so when you have only one input, then you obtain the same result as it was developed in this paper. So it means that basically here what we have just done is that we have extended the persistency criterion for the data informativity to the MISO FIR case. So we have an analogy with the SISO case. So it's quite nice. So what we are going to do in the sequel is that now, since the persistency is a necessary and sufficient condition for the data informativity, we are going to focus on the persistency of phi when U is a multisign. Okay, so if you remember, when U is a multisign, it's given by this equation here. And what I'm going to do here, I will use Euler's formula on this cosinus here, such that now I can rewrite this multisign into this complex valued multisign here, where lambda bar KL is given by this expression. It depends on the amplitude and on the phase shift, and it's called a phasor. So now by using this rewriting for each UK, I can rewrite each phi UK of the regressor phi U, given by this, into this form. So here I won't enter it in details, but basically what you do is that for each signal here, you isolate the exponential term here in one signal vector. Then you obtain this matrix here that depends on the phasors, on the frequencies, and, on the model structure complexity. Okay. So since this rewriting here is possible for each phi UK of phi U, then phi U can be rewritten into this form, where here the matrix T sin given here, it's basically the concatenation of all matrices T sin K, given by this. So just a quick word on the dimension of this matrix. So here it has two S columns because here I have two S elements in my signal. And remember that S is the number of sinusoids in my multisign excitation. And it has PM rows. And remember that PM is the number of parameters. Okay, so now if I inject phi U into this expression, I can rewrite it into this form. And remember that we are looking for conditions such that phi U is persistently exciting, and so such that this matrix here is positive definite. But the nice thing with this signal vector phi sin given here is that it's positive definite. And so phi U will be persistently exciting if and only if the matrix T sin given here is full row rank. And since the persistency of phi U is equivalent to the data informativity, then the fact that T sin is a full row rank is a necessary and sufficient condition for the data informativity. This is our new result, because the nice thing with this matrix here, is that it depends on the multisign that we know, and it depends on the model structure complexity that we know also. So I can construct it and verify the rank in order to verify the data informativity. And so this is basically what we are going to do here in one numerical example. So we are going to consider a MISO FIR system with two inputs given by this equation here. So you may think that it's too simple, but we will see that things are not so simple. So since here I have a FIR filters with a degree equal to 2, I will consider a MISO FIR model structure with also a degree equal to 2, such that then it becomes full order. And in this case, I have 4 parameters to be identified in theta. Okay, so let us propose a first excitation. So here we are going to consider a multisign excitation with one sinusoid with this frequency omega1. And so you can see that indeed both inputs are excited by this frequency. Okay, so if I construct the matrix T sin in order to verify the data informativity, I obtain this matrix here. Now let's compute the rank because we want to verify that it's full row rank. In this case, the rank is equal to 2. So it's not full row rank because here we are 4 rows. And so we do not have the data informativity. Okay, so if you use this excitation for your identification, you collect the data and then you do the identification, the model that you will obtain will be very bad. So since here this excitation doesn't work, it would be nice to know why. Why this choice here doesn't work? We want to know why. Well, because basically for a matrix to be full row rank, it must satisfy one property, is that its number of columns should be greater than or equal to its number of rows. And since the matrix T has PM rows and 2S columns, then we obtain an inequality condition on the number of sinusoids S given by this. But if you remember, PM is the number of parameters in theta. And so basically, this inequality condition simply means that the number of sinusoids should be greater than or equal to the half of the number of parameters. And this is basically the same thing as we have seen it in the sizer case at the beginning. So here we have really a strong connection between the sizer case and the MIMO case. So it's really nice. And just to understand why it didn't work before for our excitation, we have 4 parameters, but we only considered one sinusoid. We should at least consider 2 sinusoids in this case. So since we need a second sinusoid, let's consider a second frequency. And now both inputs are excited by this new frequency. Okay, so here the richness condition is satisfied. I should expect to have the data informativity. Now let's verify it. So here, if I consider the matrix T is given by this. Okay, so if I calculate the rank of this matrix, it's equal to 3. So it's not full row rank. So we don't have the data informativity. And here we don't understand why, because we satisfy the richness condition, but we do not have the data informativity. And here it's quite sad, because it seems that the analogy that we have with the sizer case is quite limited in practice. And indeed, contrary to the sizer case, the richness condition is only necessary in the MIMO case. So this will be maybe the saddest part of the presentation. But don't worry, it's not so sad, because this particular case that I just show you here, where the richness condition is satisfied, but we do not have the data informativity, is really pathological. Because in practice, the richness condition will be generically sufficient for the data informativity. To prove it to you, what we are going to do is that instead of minus 0.5 here, I consider plus 0.5 now. Then my matrix T is this following one. And now the rank of this matrix is equal to 4. It's full row rank. And so we have the data informativity. And so now we are happy. Sorry. Okay. So that was all for the linear case. I won't say anything more. I will just give a brief word of the result that I didn't explain here. So we have extended this study that I've done here for MIMO model structure, Argmax, IRIX, Bode-Jenkins, output error. We have seen that in this case, the data will be informative if for each output, a particular regressor phi is persistently exciting. When U is a filtered white noise excitation, phi will be persistently exciting if only if a certain matrix is full row rank. And this matrix depends on the parametrization of your filtered white noise excitation and the model structure complexity. And finally, we have also extended this to the closed loop case, where here you will have the data informativity if for each output, again, a matrix is full row rank. And this matrix depends on the controller parametrization and the external excitation parametrization, and also the model structure complexity. So I know that I got some comments from the reviewer on this part, more on these results here. So here I won't answer this question here, but I will be glad to answer them after the presentation. Okay, so I know what you are thinking here, that it was too easy because it was the linear case. So that is why now we are going to consider the non-linear case. But don't worry, I won't complexify the study a bit because we are going to consider this particular non-linear system. So in this case, U is the input, Y the output. Here we have a white noise, a filtered white noise. And here what you can see is that indeed we have a nonlinearity. And what we want is to estimate accurately this tree transfer function here. So since we have a nonlinear system, we should consider a nonlinear model structure. However, instead of doing this, let us observe that we can rewrite this system into this particular form. And this form is quite interesting because it has almost the form of a MIMO system with 2 inputs, except that our input vector depends on one signal, and the other signal is basically a nonlinear version of this first signal here. But except this, we can still consider MIMO model structure in order to do the identification of this street transfer function here. So this is what I'm going to do here. So here, again, I will only consider MIMO FIR model structure. And for the data informativity study, we will only consider multi-sign excitation as before. Well, then the question that we can ask, since we have considered the MIMO linear model structure, is that can we explore directly the results of the linear case that we have deduced for the, derived for the linear case, for multi-sign excitation? Well, when U is a multi-sign, U power n is also a multi-sign because here we have a static non-linearity. And so the answer of this question is quite simple, is yes, because the result that we have, is that we will have the data informativity if and only if the matrix T seen here is full rank. I can directly use the previous results of the linear case. So it's very great. Not so great, because in order to use this result here, we need to calculate the frequencies, the amplitudes, and the phase shift of U power n. And if I can allow myself some poetry, about this calculation is that it is theoretically possible, however, it can be analytically horrible. Because when U has a lot of sinusoids and when n is quite high, if you try to do the calculation, you will feel pain about it. So it would be nice to have results which requires less calculation. And so this is what we have done in the PhD thesis. We have derived results that require less calculation. Here I'm going to present one of them. And this result is based on one observation, is that the multi-sign U power n has more sinusoids than U. So let's illustrate this. So here, if I plot the power spectrum density of U, which is discrete because it's a multi-sign, then the power spectrum density of U power n will be composed of frequencies which are common in blue to the Ph.D. of U, and extra frequencies or extra sinusoids which are not common to the Ph.D. of U. And these extra sinusoids will only excite the second linear system GO2. And this is nice because it has a consequence for the data informativity, because here, another way to say it is that U power n, a part of U power n is orthogonal to U. And if this orthogonal part is enough rich with enough frequencies, sinusoids, then we will have the data informativity for the identification of GO2 alone. And if moreover, we have enough frequencies here for the identification of GO2 for the data informativity, then we will have the data informativity for the whole MIMO linear model structure. So what I mean is basically the result that I have here is that consider that U is a multi-sign with S sinusoids and denote by S2 the number of extra sinusoids of U power n, then we will have the data informativity if both inequalities here, richness condition here are satisfied. What you can observe is that it's basically the richness condition of the size case. Okay, of course, here I explain it with words and illustration. There is a formal proof in the PhD thesis. So what is nice with this new result here is that we only need to calculate the frequencies of U power n, which requires less calculation. That's nice. And as stated like this, without changing any word, this result can be extended for Bode-Jenkins and output error model structure. Okay, so that was all. I think that's all for the theoretical analysis. I think that you have enough about it. So now what I'm going to do is that I will switch to the practical work on the identification of the MIMO gyroscope. So it seems that it falls out of the blue, but we will see that there is a connection with the data informativity, so the previous work that I just showed you. So a MIMO gyroscope, what is it basically? So basically a MIMO gyroscope is a sensor that is used to measure angular rates. And it can be described as follows. So basically it's a structure. And inside this structure, you have a first mass mx that is oscillating along the x-axis. Then you have a second mass my, which is oscillating along the y-axis. And what we want here is to estimate the angular rate or rotation speed, omega, around the z-axis that is pointing toward you. So to do this measurement of the angular rate, what we do here is that we excite we can excite both masses with external forces, Fx, Fy, and we can measure both mass displacements, Xmech, Ymech for the notation. And this excitation and this measurement are done by a capacitive instrumentation called drive comps. So basically, I won't enter in details here, but basically a drive comp, as you can, it's illustrated here. So it's basically 2 comps which are electrically conductive and which are interdigitated. And so you can excite both masses and measure the displacements thanks to this. I won't enter in details here. So yes, I forgot to mention something, because what you can see here is that we have a rotation. And so this means that both masses here will be subjected to an inertial effect that is called the Coriolis effect. And basically it's a force that will be applied on each mass, okay? And the nice thing with this Coriolis force is that it's proportional to the angular rate omega that we want to estimate. So that's nice. And so here you can deduce, you can find the main idea to estimate the angular rate. So here it's a really, really simplified idea of how to estimate the angular rate. It's more complicated than this, but basically you estimate the Coriolis force on one mass, and then you use the fact that it's proportional to omega in order to estimate omega. It's really simplified. It's more complicated than this, but this is the main idea. Okay, so here you can see that for the principle it's quite easy, but the MIMO gyroscope has also some other advantages. So it's cheap, it's small, it consumes a few energy, so it's a very nice type of gyroscope. And so you can find gyroscope everywhere. For instance, you can find some in smartphone if you want to play some video games, or there is no point to it, but you have MIMO gyroscope to do this. But the problem is that the MIMO gyroscope is the most inaccurate type of gyroscope among all possibilities. And this is quite bad because here we have a lot of advantages, but we have this inaccuracy problem. So in order to circumvent this problem of accuracy, the MIMO gyroscope is often put in closed loop in order to increase the accuracy. And it is basically the goal of the next 4 months project is to develop a methodology for this design of the controller in order to increase the accuracy of the MIMO gyroscope. And since we want a controller, we need to design this controller based on accurate model of the dynamics of the MIMO gyroscope. And it's basically my job here in this project to obtain this model of the dynamics of the MIMO gyroscope. Okay, so during the PhD thesis, I only focus on the 3 main dynamics. So the mechanical dynamics of both masses and 2 disturbing effects. So here, this effect comes from the fact that we are using drive comps. And here, well, noise, because as I said earlier, there's always noise. So here we are going to estimate it in order to design this optimal controller. So if we look at the literature for the modeling of these dynamics, a lot of results focus on the mechanical dynamics because they are useful to estimate the angular rate. A work worked on the modeling of the 2 first effects here, but the problem is based on an approximation, and so it reduces the validity of the model, which is not great for the design of an optimal controller. And there is no work for the complete modeling of these 3 dynamics. So the last type of contribution of this PhD thesis is to develop an identification method for a complete modeling of these 3 dynamics. And so this is basically what I'm going to present to you. However, here again, I'm going to do a simplification that I will focus only on the mass mx, just to simplify the presentation. So I'm going to need to introduce some notations. So we are going to denote by ux the input voltage that is used to generate the force in order to make the mass mx move. And I will denote by x tilde the output voltage, which is basically an image of the displacement xmech of the mass mx. And so what you can prove by using, for instance, physics laws is that the mechanical dynamics can be modeled as a linear transfer function where the input here is the square of the input voltage. Then you can prove that, so sorry, I forgot to mention it, it's very important, but here we have a nonlinearity. then you can prove that the parasitic capacitive coupling can be modeled as a linear transfer function added to the first dynamic. And here the input is the input voltage. And finally, we are going to model the noise as an additive disturbance, and we will model it as a filtered white noise model. And so what we want is to estimate accurately this street transfer function. And what you can observe is basically the same type of nonlinear system that we have studied before in the data informativity analysis. So here there is a link between both works. And so now we have to design for the modeling approach for this street transfer function, because we can consider a gray box approach. So basically you consider first principles, and then you try to estimate the parameters by using experimental data, or you can consider a black box approach where here you do the estimation only with experimental data. So here we decided to consider a black box approach because we want to estimate all the dynamics related to this transfer function, since we want an optimal controller. So here at the beginning, we want to model everything. And there might be some dynamics, and it's actually the case, which cannot be represented by first principle equation. Okay, so that was for the big method, but in the PhD thesis here, I derived two different black box identification methods. So the first one is called SISO by SISO approach. So the main idea, I won't enter in details, but you isolate the dynamics linked to each transfer function by using the square nonlinearity in the frequency domain. And then you perform separate SISO identification in order to estimate the three transfer function. So here we will do three SISO identification. But the problem of this approach is that we have a validity problem for the model on a very narrow frequency range, which is not optimal for the controller design. And the second approach is basically, I call it the MIMO approach, because your nonlinear system, you can write it into almost a MIMO linear system, as we did during the data informativity analysis. And here the input vector is given by this now. And you can see that you can consider a MIMO model structure to estimate this street transfer function. So that is why we call it the MIMO approach. So here we had to consider a Bogdan-Kitts model structure. But the problem is that then the optimization is very highly nonlinear. So you can consider different algorithm, optimization algorithm in order to solve this. So graded addition method, Gauss-Newton algorithm, and so on. But for all these algorithms, if you want to get to the global minimum, you need to provide a good initialization. So in order to solve this problem of initialization and in order to solve this problem of validity, what we have done here is that we have used the SISO by SISO approach as an initialization for the MIMO approach. And so then we can solve both problems at the same time. Okay, so that was for the methods. But what interests us here is the design of the excitation. So I'm going to explain this design here for one approach. I won't have the time for the other approach. And here I will focus on the MIMO approach. So of course, we should design this excitation such that we have the data informativity, because we want an accurate model. And so we can directly use the result that I developed earlier in order to verify the data informativity. Okay, but I must confess something right now, because basically the data informativity is indeed a necessary condition for an accurate modeling, but it's not sufficient. Because what you have to do also is to design your excitation such that you increase the signal to noise ratio in order to decrease the uncertainties. And so this is what I'm going to present here, this design, briefly. So this design will be done thanks to prior knowledge that we know on the main gyroscope. So we know that the parasitic capacitive coupling has a high pass effect. So basically here for the design of the excitation, it's not so restrictive. It's better to put some frequencies in high frequency range, but there's a lot of restriction. For the mechanical dynamics, things are really different, because basically it's a resonant behavior with a high quality factor, meaning that the dynamics are really focused around the resonance frequency denoted by omega 0x. And so we should excite only at this very resonance, around the resonance frequency omega 0x. So like this, it seems that it's still possible. It's still easy, but hey, there's a problem again, is that the input of this transfer function is ux, and the input of this transfer function is ux squared. And so now things are more complicated. But fortunately, here we found a way to do this design. So it's more an engineering design that I'm going to present to you. But basically, we consider a multisign excitation where some frequencies are in low frequency range and high frequency range, but a lot of frequency are focused at the half of the resonance frequency. Because thanks to the square nonlinearity, we will have extra sinusoids, which will be in the Ph.D. of ux squared, which will excite the resonance. And so we will increase the signal to noise ratio for both transfer functions. Okay, so that was for the design part of the excitation, but remember that I only focus a part of the dynamics, so I need to talk about the other part here, because we have a second mass, my. So we have a second input, uy, and a second output, uy tilde. And fortunately, we have the same type of prior knowledge for the other transfer function that we can estimate here. And there's just a small difference for the mass my, is that we have a second resonance frequency denoted by omega 0y, which has a nice property to be close to omega 0x. So basically, we have the same design for the excitation uy. So that's nice. Okay, so it's time to give now the results about the identification. So since here you can see that you have 4 different transfers, then here we will have 4 different models. So here you have the board diagram, only the magnitude for the mechanical dynamics given by both methods. So here you can see the input and the corresponding output for each transfer function. So you can see that both methods give the same modeling, so that's nice. And here what I've done is that I computed the best fit that we obtained for this transfer here. And you can see that basically the best fit are quite high, except for one, but basically it seems that the model is still performing quite well. Just a word for the mechanical dynamics, you can see that some transfer functions have 1 resonance, but others have 2 resonances. Okay, and now the board diagram, so only the magnitude again for the parasitic capacitive coupling. So here again, both methods seems to give the same model, at least on this frequency range. And here it seems that there is no parasitic capacitive coupling because we have a very low gain. And so here, yes, it's the same best fit here because it's the MIMO transfer that we have here. Okay, so now we have a model. So what we can do with a model is to compute, to design the controller. So the controller design part is not me who was in charge of it. It's my one of my colleagues, Fabricio Sagin, who designed the controller based on my identified model. Here I will only present one of the parts of this controller. So in order to increase the accuracy of the MEMS gyroscope, there's something that you have to do is to remove the parasitic capacitive coupling because it's really disturbing the MEMS gyroscope. So the controller that has been considered is a feed-forward controller given here. And here you have the minus sign, and the input is the same for the parasitic capacitive coupling. So here for the controller design, it's quite easy to guess one solution. It's basically what we have considered, that what Fabricio considered is it's the identified model of the parasitic capacitive coupling. So let us verify if this kind of controller works. So here, in order to do this verification, we did an experiment where both input voltages are excited with random binary sequences. And here I plot the fast Fourier transform of the output of the mass mx, x tilde, before the compensation in blue and after the compensation in red. And what you can observe is that indeed we have a great reduction, a great compensation of the parasitic capacitive effect. And you can see that the parasitic capacitive is a really disturbing effect because before it, we couldn't see the resonance of the mechanical dynamics, meaning that the mechanical dynamics was hidden by the parasitic capacitive effect. So now we can see it thanks to the controller. Okay, now I think that it's time to conclude because I've said, I think, enough things about the work that I've done during 3 years. So basically what I've just done here during my PhD thesis can be divided in two parts. I've done a theoretical work on the data informativity, and I provide new results for for 3 cases, the MIMO linear system, for MIMO linear systems in open loop and in closed loop, and also for a particular class of nonlinear systems in open loop. And this particular class of nonlinear system was motivated by the practical work on the identification of the MEM gyroscope. And we then developed a more complete modeling of this MEM gyroscope. We designed a controller based on it, and then we obtained quite first-grade controller performances. Okay, so of course a PhD thesis is never finished. And here I give some leads for future work. So it's not all possible leads that I put, for instance, in the manuscript. Here I pick 3 of them. So first, it would be nice to consider data informativity for more complex nonlinear systems, because here, well, this study was quite good for this particular class for the MEM gyroscope, but is very restrictive for other real-life systems. So it would be nice to also extend it for other more complex nonlinear systems. Of course, here also for the MEM gyroscope, I use the prediction error method because there's something nice with this method is that you can estimate the uncertainties of the model for a level of probability. And it would be nice to estimate them and then study the effect on these uncertainties on the controller. So that would be the robustness analysis part. And it's done by another PhD student, so Jorge Ayala in the project. And finally, here, for the modeling, I only consider experiment with a non-zero, with an angular rate equal to 0, but it would be nice to verify that the model is great also for experiments with an angular rate. And here I really want to thank you all. So first I want to thank my internet connection that make it right until the end, I hope, actually. And I want to thank the jury on Zoom and the people who are following this PhD on YouTube, and also thank Fabricio for live streaming this presentation on YouTube. Well, what I want to say is thank you for your attention. Okay.
Sorry. Can you hear me now?
Yes, I can hear you.
Okay. So thank you for this, let's say, impressive presentation. Before giving the floor to my colleague, I already would like to congratulate you for the high quality of your presentation. Really, it was, we can say, easy to follow, dynamic, interesting, well illustrative. Well, all the ingredients were present for this perfect
thank you.
Speech. So, well, now it's time to open the discussion with a member of your committee. So I suggest to start with reviewers, and maybe Johan, if you would like to start to open the discussion with Kévin.
We'll just switch the slide because I have a version of a slide which have animation, so it's better for me to change.
Okay, no worries. Okay, for me. So, Johan, so maybe what I suggest is that we open our micro and camera when we discuss with Kévin, so it's easier maybe for him to interact with us. So, Johan, the floor is yours.
Okay, thank you, Marion. So good afternoon, Kevin. I also enjoyed very much reading your thesis, and listening now to your presentation made everything even clearer, because now we could enjoy those points where you put the emphasis, and the simplified explanations are also very helpful. I enjoyed that very much. I have written down a lot of questions while I was reading the text, not because it's poorly written, but because it's very interesting. And I will jump a bit forwards, backwards through these questions. So also through your text, just set by the interest that I also had, where I like to discuss directly with you. And I will start with a question on your title, because after 5 seconds starting reading your thesis, I had written down already a question. And if we read, you start with data informativity for the prediction, error identification, and so on and so forth. Now, I was wondering, data informativity, isn't it an intrinsic quality of the data and the system that is independent of the identification framework that you're using. So could you use a shorter title, Data Informativity for MIMO system identification, for example?
Ah, yes, I see what you mean. Yeah, because the data informativity is something that is indeed for the prediction error identification. Yeah, you're right. Yeah, for the title here, I just wanted to emphasize on the prediction error method.
Yeah,
yeah, you're right. The data informativity is something about the that is linked to the method of prediction error identification.
Okay, then we fully agree. Then there was a second assumption that you made, and that is, for example, page 37 in the thesis, you
Yes,
mentioned, yeah, you don't have to jump towards it. You mentioned that the system is assumed to be stable. Now, assume that I have an unstable system that is stabilized in a closed loop, and I want to work on that. Can I still use the framework, or is everything lost?
No, because when you write the equation, we need this assumption in order to define. I will just give back the here.
Yeah.
For instance, because basically when you will perform the identification, you will have G0. Okay, but here, if you don't have a stability assumption, this can be equal to this can't be defined actually. This limit can't be defined if you don't have a stability assumption. That is very fine.
And do you think it would be possible to, if you would get more time, to extend your results to deal also with unstable systems captured in closed loop?
Yes, you can. And one possibility then in this case is that you don't do the direct closed loop identification, but I don't have a, yes, I think I have a closed loop scheme somewhere in my slides. Wait, yes, here. Okay, so here, the identification that I consider is I consider input, output data directly to do the identification. But if you have a system that is, that is unstable, then you can't do it directly like this. Otherwise, the limit is not defined. But what you can do is that you can estimate the model from R to Y, so the closed loop model. And then thanks to the knowledge of the controller, you can then estimate back G0.
Okay.
Like this.
So that would be indeed a possibility. Good. Then I jump to the informativity of multi-sign experiments. And you explained also in the presentation, look with 1 or 2 signs or some signs, we are on the safe side. If not, we have a problem. Now, in practice, when I do an experiment, I do not always wait for the steady state situation where all transients are gone. So if I start measuring from the beginning, including the transient response, can I say more? Can I relax the conditions that you have presented here?
I think yes. And I actually, when I did some simulation, I observed that sometimes, yes, even if I don't have a data informativity, but I only consider the transient data, sometimes you find directly you find a very close estimate of the system. Yes, this is a really interesting question, and it's something that I ask myself. But the problem of the data informativity here is, again, because of this operator, that your transient will disappear in this sum here because it's a limit. But in reality, you have, I think that you have more information thanks to the transient, and this should be considered as also a possible future lead. Yes. But data informativity, it's not here because of this operator.
So actually, you can consider your transient as the response to an additional impulse, which is a wideband signal, and so excites the system at many, many frequencies at the same time. Okay, then I like to jump to the gyroscope.
Yes.
And one, maybe we can look to the equations there.
This one?
Yeah, where you can see you decoupled both masses.
Yes.
But in practice, are you sure that this decoupling is perfect? And
no.
What if it's not like that?
No. Yeah, I have. If you consider the first principles, I have right here. First principle of both masses you have, you can see here you have the first principle on the mass mx. And you can see that actually the displacement of the mass my interacts also in the dynamics. So you have cross-coupling dynamics.
Mm-hmm.
So of course, it's not really a good idea to do it like this, but if it's linear, the way how I do it should not change how I can estimate. If I do this estimation separately, if it's linear, of course, they should not have differences. But this is a really strong assumption that I made here. But actually, I tried by doing a MIMO experiment to also consider in the same time cross-coupling. And the problem is that if I consider, for instance, the Bode diagram, here, this mechanical dynamics can be hidden by this one. And so I got some problems during the optimization. Even if I initialize well my optimization with this model here, I got some problem. So I had to decouple because of this. And it's the same thing with the parasitic capacitive coupling. Here you can see that you have a very strong gain with respect to this one.
Yeah. Shouldn't it be safe then to check on the real device if this cross-coupling can be neglected or not?
Well, in this case, the model that I have here for this MEM gyroscope, here we have quite a huge coupling here. Normally, the Bode diagram should be have a gain less important, but in this case, no. So here we should consider them in the controller design because so it's something that I write in my PhD thesis that this cross coupling have then an error in the estimation of the angular rate if you don't consider them. I don't remember who is it. If do you want me to show to you or
no, it's fine. I prefer just to. I feel where we are heading to, and that is satisfying me. But I like to continue now with the gyroscope, and maybe if you can show slide 34.
34. So this one.
No, go back one more. It's this one here. So you explained nicely that the idea is that you try to decouple the input ux from the squared input ux squared on the right side. And then you start to play with the spectra. Now there is in this case, it's a special case because you only have u squared, which is an even nonlinearity. There is also another possibility. Assume that with ux, I excite only the odd frequencies.
Yes.
Then where will we see the frequencies in u squared? At what frequencies will we excite the system with that signal?
So here, if I have frequencies here, well, the frequency will be...
For example, ux excite frequency 1, 3, 5, 7, and so on.
So you will have, of course, because this is in discrete time, so for the data, this frequency will be then. So if I plot them like this, but in reality, there is the anti-aliasing filter.
Yeah, so, but that will not hurt us. So if I excite the odd frequencies, 1, 3, 5, the signal u squared will be present only at the even frequencies, 2, 4.
Ah, okay, yeah.
And so that is a very, very simple tool to come up with a very easy to design experiment for you. I use a broadband excitation in the frequency band of interest with only odd frequencies, and then I have a robust signal to identify the first part of the system, and then the even nonlinearity that is acting at the even frequencies. There I can see the second system, and even if the resonance frequency would start to shift, I'm not very sensitive to it because I excite the system everywhere where it might be of potential interests.
Okay, yeah, I understood. Yeah, what you said. Yeah, I could have done it. I don't know why I didn't do it like this. So yeah, I don't have an argument for it.
And it fits perfectly with all the theory that you have developed.
Okay.
Okay. Then at a given moment, when you were discussing the results of your theorems, which I liked very much in your text, so each time you explain carefully to the reader what's the impact of the assumptions and the results, you show in your thesis that a possibility is, as we just did on the gyroscope, is that each input uses a unique set of frequencies.
Yeah.
Each frequency is assigned only to one input.
Yeah.
Now, if we look now to it from a practical point of view, is this a choice that is free, or do you pay a price for it? Is it a free lunch or not?
Using orthogonal multisign?
Yeah, we also call it separate multisigns or whatever.
Okay.
So it's a very attractive idea, but does it come with a price?
In my case, for the data informativity, no.
I agree.
Because it's quite easy.
But that's a theoretic concept. If we bring it into practice.
Yes. Well, it depends on the restriction that you have on your system. Here, I don't have a choice because I have U square. So I have always frequency, my multisign can't be orthogonal. That's the, well, it depends, but mostly you have to be careful on this. But for the, in order to answer your question differently, I mean, if you want to do an experiment design, it might be restrictive if you consider this type of way to do it.
Well, where you will pay a price is that assume that you have 5 inputs. Then for input 1, I can use only, for example, frequency 1, 6, 11. For the second input, I use frequency 2, and each time I jump with 5. A step of 5. But when you look now to the measurement time, that's linked to the resolution of your multisign, and you make multisigns with gaps. On each channel, you have a sparse multisign, and in order to make the gaps small enough, you need a long measurement time. You have to increase the period length to keep the frequency resolution high enough. And so that's the backside of this theoretically very attractive solution.
Oh, yeah, okay. Yeah.
In an identification experiment, if I excite all frequencies, but then of course we have to check that it's still informative. But if I excite all frequencies, I can use shorter experiments. So that's a practical aspect that also comes in while you're designing your results.
Yeah, that's a very great way to say it. Because I got some comments from reviewers from my article who say that why using this type of multisign, but I didn't think of this. Yeah. Thank you about the.
Then I have another practical question, and I just opened my text. It's on page 132, where you design the practical experiment on the gyroscope. And
I have a problem with. Sorry.
Yeah. Okay, but I will put my question. I guess you will remember what's going on.
Okay.
So first of all, I really was very glad to see that you had a theoretical part and an experimental part, because that shows that you have nicely balanced results on both aspects. But when I started to look into the design parameters, I made some calculations, and from the numbers that you gave in the text, I have the impression that the length of the experiment is only one time constant of the system. And that scares me a bit. Maybe I was wrong, or I used wrong numbers. But for example, the optimal input for a first order single input, single output system is that you have to measure at the 3 dB point of the system, which means that you have to measure in the order of 6 time constants. If you go much shorter than that, then from informative point, so the data will be informative, but then if you start to look to the noise sensitivity and the efficiency, we are really on the bad side.
Yeah, you're right. Yes. So here we have a very high sampling frequency. And so in this case, you can see 62,500 hertz. And so it's quite high, because then if you consider, for instance, only 2 seconds of experiment, you have already more than 100,000 data. So
yeah, The problem that you might get is that if you sample fast, you get a lot of points, but you also have to measure long enough to see how a slow system is reacting. Otherwise,
I know.
you just see a very small part of the results.
No, you're right. And it was a restriction because we could not change the resonance frequency, and we had the sampling frequency, and we had to change this. So yes, here it's true that I only saw a part of the dynamics, but on the contrary, we really wanted to have a model for the high frequency range mostly, because the resonance frequency is more in the high frequency range, near to the Nyquist frequency.
Mm-hmm.
So I think that it was not a problem because it seems that it's working when we do the controller, but I understand your concern here. But if I wanted to do it as you said, I needed to consider a very number of points, and practically this is not suitable for an optimization. I tried sometimes to use 1 million of data, but then I had to wait 1 hour to get the results. So
yeah, but that's you have to make this design only once, and maybe it's better than to calculate for 1 hour and to come up with a perfect design or a very good design than getting your results in 1 minute, but coming up with if I put it extreme, with a sloppy design.
Yeah, maybe well, it depends, because here the idea is to provide at the end an identification method that then the industrial will use in order to manufacture gyroscope. And if you can do it faster and still get an accurate model, then we can do it like this. But yeah, you're absolutely right. It would be nice also to consider a longer experiment just to verify that I don't have a problem with the identified model that I have here.
Okay, and then I see that my time is running fast. A last question. You have delivered sufficient conditions, and you also emphasized this during the presentation. What if you would get a postdoc of 3 years? Do you think it would be possible to turn it also into necessary conditions, or don't you believe in it?
No, it's not that I don't believe in it, but well, I would just need to find. Can you see again the slide? Yes.
Yes.
Okay. Well, the problem really to get necessary and sufficient condition, if you read is that we have condition like this. I can resume it like this: is that you have to verify that the matrix is full of rank. But the data informativity can be rewritten into this formula. You will have the data informativity if for all delta in a set, this is true. This equation has only one solution, and it's this one. And another way to say it is that the kernel of the transpose of this, the null space, the null space of this, the transpose of this matrix inter the space here is equal to 0. But the problem is to characterize this space D, which is linked to the model structure. And this is not really easy. And actually, I found recently it was 3 months ago, I found that for the IRIX case in closed loop, it's also a necessary and sufficient condition. I found this new result. But for the other model structure, I need to characterize this space D in order to conclude if it's a necessary and sufficient condition. And this is not easy to do. So I'm not sure that you can find an easy solution to do it. And with a postdoc, yeah, maybe I can try, but it's not that I'm not optimistic, but I don't know if really you will find something, because really this set D can be really nasty, really complex, another way to say it.
Okay, so thank you very much for the discussion, and I pass the word back to our president.
Thank you, Johan, for this interesting discussion. So now let me give the floor to Guillaume.
Okay.
Guillaume, are you here? Yes.
Yeah.
Okay.
Yes, I'm here.
Okay, good. It's your turn.
Can you hear me?
Yes.
I don't know if you see my face. Yes, you see it.
Yes, we can.
Wonderful. So first of all, I would like to thank Laurent and Xavier for inviting me to be a member of this jury, because the document is huge, but it's very interesting. So I really appreciate the document. And so first, I would like to congratulate you on that. And second, during your presentation, it's clear that you have a lot of enthusiasm. So please keep it, and especially if you want to teach, if you want to become a professor, keep it, because it's very, very good. So that's the first point. So just like Johan, when I read your document, I wrote many questions, but finally, by listening to you during your presentation, I've got other questions. So I'm going to start with that. And if I've got time, then I'll switch to the document. If we can go on the first slide, the title. I'm going to talk about the title as well. But I'm going to talk about the MIMO case, the MIMO system. And so I worked only once with a PhD student during 3 years on MFDs. And I remember that it was a real pain in the neck, especially when you've got many inputs and many outputs. So, and usually when I have a MIMO system, I try to switch to a state space representation.
Yes.
So I would like to know if you've got an idea how to extend some of your results, or all of them in the best case, to state space representations.
So yeah, this is quite complex. I thought about this question. Well, because it's better for MIMO system to represent it in the state space. It's more stable for computation, and yes, we know that. The first problem with the state space representation is that you have to fix a bit the structure, otherwise you have an infinite number of state space representation. So that's the first point. But even in this case, so why did we consider transfer function? Really, I don't have a strong response to it, because in MATLAB, it's possible to do it like this. So that was our first motivation to do it. So, and I was more used to transfer function than state space, but we know that it's better for the MIMO representation to use a state space representation. I think that for the extension of the case of the result to the state space form, is that now you have to deal with matrices, and yes, also in the case for transfer function, but here you have matrices with your parameters, and yeah, I don't know. I tried once.
If you read, so it's true that I don't play with transfer function so much, but you have many results where you can show the link between Rmax models and state space representations. So my question is, can we try to find a way to extend your results from Rmax to state space?
I think maybe because you start from this definition, and instead of G, it's more complex, but you have to put something else here. I think it might be possible. I don't know.
Okay.
But I think it might be possible.
Okay. Then let's go to slide number 6.
6.
Yeah, this one. I liked it very much. And let us assume that for specific reasons, you're not able to excite your system that well. So you are in the first case. And let's say that just like your ranking, you've got 5 models in the end.
Okay.
And how do you select, I would say, the best one afterwards?
Well, the first possibility is that if you have prior knowledge, they might help you to find the good one. And I think so. I think that's the only thing that I can think of or discriminate.
What about the sparsity, or do you think that in the end, I would say you will have a model with a smaller order or with small values if you compare the estimated coefficients? I don't know. That's an open question, but.
No, I don't think so, because here, well, I said that you will have several models. Here it's in the asymptotic way. So here with the uncertainties, if you don't have the data informativity, your estimator can converge everywhere where you want. So I think that there is only the prior knowledge that can help you, or if you change your excitation.
Okay.
I can't think of another way to discriminate them. Yeah.
Okay. Then let's go to slide 17.
17. This one.
Okay, yeah, this one. So as you said very clearly, you're going to test the rank of a matrix. And according to my experience, when I play with matrices, usually I've got ill-conditioned matrices.
I know.
And so I test the rank, and it's not as good as I wish. So do you have experienced some results where this matrix is ill-conditioned, and so it's complicated to conclude?
So for this one here in particular, no.
No, not this one in particular.
But for the closed loop case, once when I wanted to consider, I considered the Bot-Jenkins with 3 inputs. So here I got like a matrix with 20 columns and 17 rows. I don't remember, but yes, the rank was not good. So no, indeed, the rank computation is not very great. It's not great at all on MATLAB if your matrix is ill-conditioned. But I have an answer to this, because basically it means that you are very near to be non-informative.
Mm-hmm.
And this will have an impact because your uncertainties will be very high when you will do an identification with a number of data, a reasonable number of data. And so you may also want to change the excitation in order to get a better uncertainties. So yes, if you are at 1 epsilon to be full row rank, but your rank computation cannot see this epsilon, it's still better to change your excitation.
Okay. And it's related to this slide, I think. Yeah, you've got the hyperparameter M. Okay, so you select it before AND. But in practice, when you have a real system in front of you, you don't know M.
Yeah.
So how do you cope with this unknown M, or do you test many possibilities? How do
Yes, you do it iteratively because you can verify the full order assumption of your model structure by doing some residual test on the prediction. On the prediction error computed at the identified parameter vector. There are some tests that exist in order to verify this. So he just wanted the user design an excitation, and now he wants to test different model structure. And at each time, he has to wonder, will my excitation be enough with this model structure? But of course, he does not know the real, if I can say so, the true model structure.
Okay. Yeah. Then let's go to slide 31.
31.
Where you talk about gray box.
Yeah, so it's here.
Yeah, you talk about gray box, and you said that if I'm correct, you said that okay, you can play with a gray box model, but finally you cannot guarantee that the selected model structure is strong enough to represent your data or your real system. So you switch to the black box model.
Mm.
That's am I right, or that's
yeah, that only for the determination of this future function, because here in this model you have already some gray box things because we have the square of input voltage that comes from. But yes, it's exactly as you mean it.
Okay, but and so then you said that if you want to solve the problem directly, it's a nonlinear optimization, so it may be tricky. And so your idea is to find an initial guess by using this SISO by SISO approach. And what about using a gray box approach where you have prior on the parameters, so you can constrain the optimization by using bounds. And from this gray box model, you have an initial guess for your nonlinear optimization problem. Is it doable or not?
So in my experience, because the manufacturer of the MEM gyroscope gave us some gray box parameters, I can show to you which one is one. We had some parameters, but it was not corresponding for our MEM gyroscope, because when we did the first identification, we compare both resonance frequency from their model and from what we estimate, and it was very far. So here the gray box was not really a good idea using the gray box model, because here, since you have a high quality factor for the resonance, you should really initialize well the resonance frequency in your optimization. Otherwise, it will be bad. This is basically what I experimented. And the second thing is that there is, if you only want to, you could do it, but and actually chronology, how to say it, at first started to use gray box identification, switching to the black box. I tried, and then there was this unexplained effect that we couldn't understand. For instance, here you have a resonance frequency. You should expect a phase shift of minus 90 degrees. Phase shift that we obtained was not minus 90 degrees, and my gray box model was not able to fit this, and I got really problem for the optimization.
Okay.
So yeah, it was better to start with a black box in this case. But I understand your, and I think maybe for the CISO, I didn't met any problem for the CISO by CISO approach, but even here you have some non-linear optimization to do, and you can maybe use your parameter to initialize. I'm sorry, that's
that's fine. That's fine.
Pronounce.
No worries.
So you can use it to initialize the CISO by CISO approach. Then for your mind, yeah, it's possible, but in my case, it didn't work for the MEM gyroscope that I had.
Okay. So I'm going to ask only 2 more questions. Do you think that, so in this document and in your 3-year project, you worked only with discrete time models, except the gray box, but okay. So can you extend your results if I use a continuous time model, or is it exactly the same? Just copy and paste, or do you have something to modify?
It's exactly the same, because no, I'm not sure that it's exactly the same. But I don't have a lot of experience on the continuous time modeling. So here I can't really answer your question very well, but I think that some adaptation to do. I know that if you want to use some continuous time method, sometimes you need to add instrumental variables, or otherwise you have problem of consistency. But here, with the discrete time, the problem of consistency is solved with the data informativity. So I don't know. Really, I don't know.
Okay. I'm sure that you will have a nice discussion with Marion on that. Just an introduction for the questions of Marion. And the last question is about the extension for, let's say, nonlinear systems.
Yeah.
So a good trade-off between linear and nonlinear is what we call LPV. Okay, linear parameter varying. And in your case, in your system with the gyroscope, you've got this omega. Okay, and I guess that, I don't know, I'm not familiar with this system, but I assume that if you've got different values for omega, you've got different linear models. And so it could be selected as a scheduling variable. And so you could extend your approach to LPV. So do you know if it's easy to extend what you developed for the informativity, for the data informativity to LPV systems? Do you have an idea?
I know that it's working. If, for instance, if you have 2 different approaches with LPV modeling. If you do the local approach, well, basically you repeat the same condition for all your modeling, you verify your data informativity. For the local approach, I know that there are some results about it. But I don't know them exactly. But in your case, for the omega here, you don't need an LP, at least if I consider if my gyroscope only works with first principle. It's not really the case, but you can see that basically omega is here. It's non-linear, but with the control objective that we made here, we can estimate it. And so we don't need an LPV model in order to estimate it. And I think that it's not a great idea, because you will have a very complex controller at the end. However, for the LPV modeling, we use it for a last dynamic that I didn't consider here. It's the temperature dependency dynamics. So here in this case, indeed, an LPV model might be a very good idea to use it, because the parameter that you have here change with the temperature. And so one possibility is to use this approach by doing several LTI identification for different temperatures. And actually, I did it after sending you this manuscript. I did some experiments, and I did an LPV modeling with the local approach by using the same result for the data informativity. I think it's possible to do this link, and I did it for the temperature dependency.
Perfect. Okay, thank you. I think I can stop here. It was very interesting to talk with you.
Thank you. Yeah, it was the same for me.
Okay, thank you, Guillaume, for this interesting discussion. So now after the viewers, I suggest that maybe Okan take the floor, if Okan is well connected.
I hope so.
Okan, you are, yes.
Okay, so yes, I'd like to start by thanking Xavier and Laurent for inviting me. This has been very interesting to read the work of Kévin and listening here. Firstly, I'd like to congratulate you on the very nice presentation. It was outstanding, really. So very easy to follow, and can just follow up on Johan and Guillaume's comments there. I also think that the topic you have chosen is highly relevant and important, and also this that you have combined a theory with practice. I think that is really what makes a difference, where you show that you manage both parts, because one without the other is not much worth. Also, the thesis in itself was very easy to read. In fact, when I first opened it, I ended up on some pages with massive indexation, and so I got really worried there that how I get through this. But in fact, you have managed to make also these technical parts very pedagogical. So thank you for
Thank you.
That you have made.
So it was chapter 4 on the closed loop case?
Yes.
Yes, okay.
Yes. And I can also comment on the gyro application that I think you did also very well engineering work there. So I see it's very systematic and nicely done, and you also got nice results there. I also have some questions, of course, and some have already been covered by my fellow. But there are still some things that I would like to discuss. And firstly, maybe the topic you have chosen is informative data. And the first question is really, if you don't have informativity, is that necessarily a bad thing? You always want to have informativity, and yeah, can you comment on that?
It depends on the application of what you will do with your model after it. If, for instance, you want to predict a behavior with the same input with the same experiment, I think that modeling with a model that does not model all the dynamics is not a problem. So it depends on what you want to do. Here, what we really want to do is to model all the dynamics. So here, yeah, the data informativity is really in this case. And yeah, actually, here the data informativity that we studied, it's called the total data informativity. Because what you want here is that all predictors are different between them. Mm-hmm. But basically what you mean is that all predictors are different from the one evaluated at the true parameter vector. So you maybe need a less demanding condition for the data informativity. It's still called the data informativity. It's called, I think, local data informativity at theta 0, something like this. But yeah, so that was for the technical part of the data informativity. But to answer a question, I will say that indeed, it depends on what application you will do with your model.
So one aspect that you have been complaining about here in the presentation is that you had problems with optimization.
Yeah.
Expect that by the data informativity.
For the optimization? Yes, of course, because it will converge to something that you don't know. It's that you don't know. It will converge without any probability to a value that with a probability equal to 0 to a value that.
My point is a little bit here that even if you don't have informativity, the model cannot move anywhere. If you still put in some excitation, there will be constraints.
Yes.
Suppose you are after the frequency response at a certain frequency. What would you do practically?
Yes. If you only want the frequency response at one frequency, yeah, you can consider only one sinusoid. And in this case, you don't have to get the data informativity because all your model that you will obtain will have this nice property of having the same value for the frequency response at this frequency than the true system. Depends on what you need. If you really need 1 point, well, you can not have the data informativity, or you can maybe reduce your model structure such that you take only what you need. And then you will still get one model. If you want 1 point for one frequency, 1 point for your frequency response, what you can consider is an FIR with a degree equal to 2 parameters. Yes. You consider a multi-sign, even if your one sinusoid, even if your model structure is not full order. And then in this case, you will obtain one unique model. Of course, there is bias, but there will be only one unique model that will have this information that you want about this.
Exactly. So this is what I'm after. Very, very nice. So I have a motto that says, be careful with what you excite, because you will need to model it. Because if you have excited something and you don't model it, then you will have the problem you mentioned just a while ago here, that you don't know what the model you will end up with there.
Yeah.
So, okay, excellent. Let me see now. I have my questions on your PDF documents. I'm moving back and forth here a little bit. Yes, we can maybe follow up also on the optimization. You mentioned this in the MEMS application. But at the same time, a while ago, there was a discussion about subspace models. So why didn't you use a subspace model here?
I tried at the beginning, and I didn't get great results. If I did something bad or not. I know a bit subspace. I'm not an expert on it, but I tried at the beginning also subspace, just to deduce the order of my model. But I got a model that was not great.
Mm-hmm. Okay.
We don't have the reason about it.
Okay, so that's interesting to know that was not in the thesis, I think. Of course, there are also other methods that don't do nonlinear optimization, as in PEM, that one can try in a case like this. But I mean, your approach that you did here, I mean, that's of course one clearly workable approach to take it step by step. Okay. Next thing, I was a little bit curious here. I'm jumping a little bit in the type of question. So what result? What was the most difficult to obtain here in the thesis?
I would say the closed loop case was quite complicated.
Yeah.
I mean, almost the formulation. Because then it's basically putting transfer function on the same denominator, something like this. So, but yeah, I think maybe the most difficult part, I would say this, and also for the MEMS, we had this problem with my black box model with a higher order. And at the beginning, if you compute I say it here, but if you compute the rank, not the rank, sorry. I'm about rank verification of data informativity. If you compute the order of black box model for the mechanical dynamics, we obtain something very high, So 12, I think I remember. I don't remember exactly the order, and it was too high for the controller. And I spent a lot of time to understand how I can really reduce the order. So that was maybe the second difficult part. Then I consider this gray box approach in order to solve this problem, but that was not easy to find first.
Yeah.
Because of this extra dynamics that I don't know, that I did not know where it come from. Because the gyroscope is implementing on an electronic card, and apparently this has also some extra dynamics. So I think it was also the second worst part that I had during my PhD. I can say it's like this.
Okay, yeah. Interesting. Then one thing that never ceases to surprise me is that there are so many things still undiscovered in this field of linear system identification. And this is a field that's been around for almost 60 years, and a lot of people have worked in the field and contributed, but still it's possible to find areas like you have done here that have still not been solved. So I'd like to probe a little bit back in time, and because an important part of a thesis is also to give the background of what has been done in the field. So in the presentation you said that you said something about that the sizer case had been completely solved. Is that correct?
No, well, what I mean by this is when you consider the classical model structure of the sizer case. FIR, IRX, Rmax, output error, Bud-Jenkins.
Are these completely solved? So there are if and only if.
It's a if and only if, yes. It's in the paper of Reverse, the one that I cited here. It's a necessary and sufficient condition. And if actually you apply this result here to the P equal to 1, you obtain the same thing as Reverse. This one that I showed here. Yeah, here you have a necessary and sufficient condition. I think I think that everything has been said for this model structure, because it's basically a necessary and sufficient condition.
Okay. Another question I had there, because you were citing Gevers and
Here.
Several papers. You're also citing Jung's book, yeah, from.
Here, maybe I don't remember if I did here, but yeah, I should have cited here. Yeah.
You have a citation there, but I'm wondering. I'm missing a reference in the thesis on this type of persistence of excitation, informativity.
The one of there's.
You cite a number of papers from the 70s that did work on this. That was mainly the papers you cite are mainly closed loop, I think.
Yes.
There's one paper I miss. Do you know which one I'm missing?
In this in the 70s. In the
70s, yes.
No, I don't see which paper you refer to.
So what the origin of the prediction error method?
What? Sorry.
What is the origin of the prediction error method and the theory of that method?
Jung. The paper of Jung in the 70s.
So Jung had a paper on consistency of the prediction error method.
Yeah, in the 70s. Yeah.
Did you read the paper?
I read it, not entirely, because it was mainly, it was quite complex. It was another formulation of what I've used to, but yeah, I this paper, I read a bit. And so yeah, we decided, it was the same thing for the article that we published. At first, I cited this paper, and then we say that everything that was interesting about our study was in the book of Jung. But yeah, I'm aware of this existence of this paper. It's something like on consistency and identifiability. I think the title is something like this.
So it states a persistence of excitation condition in terms of the signals, and then he has a consistency result there. I think that could have been mentioned in the thesis here, because you want to follow. Now we get the impression as a reader that these results came much later, in fact.
Yes, okay, I understand. Yeah, okay. Yeah, you're right.
Okay, let's leave that. Yeah, I have some very minor. Let's see. Let me have a check on my time. Yeah, I don't have so much time left. I think I try to focus on questions, but I will, I think, in the interest of time here, skip that. Yeah, so we can move to the nonlinear part, the Hammerstein. That is maybe interesting. You had this. You didn't cover it in the presentation, but you had Gaussian white noise.
Yes.
One result.
Yes, exactly.
And yes. I think you mentioned in the conclusions that one maybe could extend this.
Yeah.
That could be. Do you think it's possible? Have you had some ideas around that?
So I tried when my filtered white noise is with an FIR and with, for instance, a U power n nonlinearity. Yeah. And it went very bad. I tried by directly doing the calculation like this with a U power n, but no, it was very bad. So I said that it would be nice to extend it, but I don't know how we can do it. I tried it, yeah. So
have you heard about Busgang's theorem?
Yes, for the best linear approximation method. Yeah,
yes, yeah. So that these works build on that result, which is an old result. Do you remember what it is?
No, something about, I think, the power spectrum density, or I don't exactly the results.
So it says that for Gaussian noise, the cross spectral density, if you have a static nonlinearity, is proportional to the spectrum. And the factor there you can compute. It's the expected value of the derivative of the nonlinearity. So I think you can play around with that, and that's not restricted to white noise. So there you have a tool to work on this.
Okay. Yeah, maybe yes.
Okay. Let me see here. Yeah, there was you discuss at several places that well, you have some degrees of freedom in your design when you design informative inputs, but then you discuss random choices and so on. Which to me sounded a little bit naive. So have you any more thoughts on that?
Yeah, here, because the thing that we wanted to prove, but we still do not have the right result, the right proof, that we wanted to prove that indeed there is a measure of pathological cases which has a zero measure. And we could find the right proof of this, so we only show this random example here only to emphasize that it seems that it's the case. It seems that indeed it's a zero measure set of pathological cases, because our random try draws didn't find a case where the informativity was not satisfied, was this, because it would be nice to have this formal proof, but for now we didn't find it. So it just like this, just to prove that indeed it seems that you will do your choice. It means that you will have a very bad luck if you have in a case where the richness condition is satisfied, but the data informativity is not satisfied.
In fact, I was very pleased to see then in the application in the MEMS gyroscope that you in fact took other considerations into account, like the crest factor, because that I think is what you would, things like that is what you would like to use the degree.
Yes.
So I was very pleased with that. But when I read these first chapters, I was a little bit confused there.
No, it was just to illustrate this zero measure that we guess about it.
Okay. Yes. Let me see if I have some last questions here. Yes. Two concluding questions maybe here. You have assumed here in the thesis that you have no under modeling. So the true system is in the model set.
Yes.
Or so do what about the case where you have under modeling? Have you thought about situation? So for example, let me point to suppose you have open loop and you have a good model of the dynamics, but you're not modeling the noise. So let's say the true system is Box-Jenkins, but you just use an output error model. Well, are your results still valid in that case?
Yeah, because what you can see is that for the Box-Jenkins case in open loop, you see that you will have the data informativity of the noise that is already, or the noise transfer function that is guaranteed. And you can see that the data informativity here depends only on the transfer function G. So even if you have, if you consider under-modeling as you propose, and it's basically what I've done here for the SISO by SISO approach, you will still guarantee the data informativity, but then what you can't define is the consistency for the parameters linked to the transfer function linked to the noise. Because the nice thing with the Box-Jenkins property is that both the parameter vectors in G and in H are different. They are independently parameterized.
Yeah.
Because I think that you will still have the data informativity for the parameter in G, and it was actually the case that I had in the SISO case, because it seemed that the model, indeed, the only model that explained my data was the one with the resonance. So it seemed that it was okay. Yeah, so I think, but it's Box-Jenkins output error, but for IRIX and Armax, you will have problem, I think.
I guess you don't need even to have a diagonal noise model in that case.
Yeah, also for the, yes, indeed.
So
in the Automatica paper, there is no assumption on the diagonal arch, but it was
okay.
But it was for the Armax model structure where now the assumption is needed, and for the closed loop case, so it was just a unified assumption for both studies.
I have the final question I have is as you know, there has been a lot of work on kernel methods during the last decade. So what about that? Yuan opened with a question about data informativity, if it was connected to just the data or a particular model. So when you use a kernel method, do you need informative data or not? Or what's your take on that?
Yes, with kernel regularization, yes, indeed, it's a good question. Well, kernel regularization is...
my point is there that you know, you have the prior and then you will singular matrix. So everything is looks fine. Is it?
Yeah. Yes, that I don't know. Maybe it's just a guess, but I don't know. But maybe your regularization will contribute to the fact that you will only have one model that will optimize your whole criterion. That's it's true that I didn't consider kernel regularization possibility to include prior knowledge. I have a guess, but I'm not sure about it. that maybe the data informativity in this case won't be needed if your prior that you have with the kernel regularization is enough, is here to complete the lack of informativity, but I'm not sure. It might be.
Okay, yeah, that's fine. Thanks. that supports my view. So, yeah, thank you very much, Kevin.
Thank you.
We'll have a chat with you.
Thank you.
To Marion.
Okay. Thank you, Ken. Well, I think I will take my turn before giving the talk to your promoters. So, well, first of all, as my colleague, I would like to thank Xavier and Laurent to have invited me to be part of this committee. Oops, sorry. Okay, to be part of this committee. Since it was a real pleasure to read your thesis and a wonderful job to hear you presenting your work. As Guillaume said, it's really nice to see a positive and dynamic attitude during this kind of presentation. So, well, can you hear me?
Yeah. Yes, I can hear.
Okay, because I cannot hear you. Okay. So, well, when you are the last one to ask questions, for sure, a lot of the questions have been already covered by my colleagues, especially the unstable system, the state space, the full order was really interesting. And well, but it was nice to hear your answer to these questions. Let me first focus on the closed loop chapters, closed loop identification chapter. So, for sure, the first question is, what are your results if the process is unstable? So you have already answered this question. But to follow a little bit the same idea, so you choose to work on the direct approach, right? So the direct approach consists in using U and Y to estimate directly the system as if it is the case as in open loop case. Okay. But here in your results, you need the knowledge of the controller to apply your method. Okay, so I have two questions. What can you say about your method if the controller is not known, is unknown? And the second question is, if the controller is known, what not using it during the identification step, not only U and Y, but using the knowledge of the controller, since you have it. And then the further question is, if you know your controller, if you use your knowledge of the controller for the identification step, don't you think that your result about informativity of the data wouldn't be different? I mean, if you use the knowledge of the controller, don't you think that your result can be a little bit different? So, sorry, my question is twice.
Yeah, I understood the first one. I will first answer the first question because it was basically one of the questions of Guillaume. And I prepared the slide on this is what can we do when the controller is unknown? Okay. So my proposition, but it's one, is try to estimate your controller. And I'm going to explain why. Because let's suppose that there is no external excitation to simplify this the explanation. Because basically, so here you have a MISO case. But here, but it can be also for a MIMO case. So basically what you do is that Y is minus Y is the input of your controller and U becomes the output. So it's a change of input notation. Yeah. And the nice thing is that you measure it and that also you measure it. So for the point of view of the controller, if you want to do an identification, it's like you don't have noise. No, because here in the assumption that I made is that there is no noise on the input here. So if you want to do an estimation by using directly your data, it's quite simple in this case because you can consider a predictor of this form and a model structure for your controller. And then if we want to estimate it, you need still to provide the data informativity. And here I did the calculation here, but I'm going to explain it another way. Is that there is a result in my thesis that says that if this signal here has a positive, it's not my result, it's the result of the literature, but if this power spectrum of this external excitation is positive definite at almost all frequencies, then we have data informativity for both transfer function. Well, it's just the same thing. If you now switch to the controller point of view, you can see that at its input, you have something that is exciting it with a power spectrum density, which is positive definite at all frequencies also. So here you will have the consistency if you try an identification by considering a model structure and then taking, so in this case, input, output data. And the thing is that since there's no noise for the point of view, I don't know if I'm clear about this, because here you have.
Well, I don't fully agree with your assumption that you have no noise, since your noise is in the loop. So since your controller is
in the loop, but this you know it actually. Why you entirely know it? Because it's not that you entirely know it, but you measure the right data, and here also.
No, but you measure the data which. Well,
why
is already corrupted by noise.
I'm not explaining it very well.
No, okay.
Is that? Yeah, I don't know how to explain it such that I'm clear about this, because here in this case, when you want to identify H0, you don't know E, of course. But here you have the nice thing that Y and U are known for you for the data at least. And of course, if I don't have this noise assumption of on the input, basically the set of data that I just need is Y, the input of the controller, and also U, which is the output that is computed by the controller. So I know also it.
Okay.
And so.
No, okay.
I don't know if it's clear. Because then,
okay, I understand that you say that okay, if I don't know the controllers, I can reconstruct this knowledge by a first estimation for sure, like in the two-stage method, for example. Yeah.
And I think that it will be exact, this estimation, if you have the data informativity, but I can't explain to you why.
No. Okay. And what about the second part of my equation? I mean, if you know, since you know the controller.
Yeah.
If you use it during the identification step, wouldn't your result be different? About
what do you mean by using it during the identification step?
I mean, not using a direct approach or putting some prior knowledge. You can whiten a little bit the signal when you know the controller, for example.
Yes. Yes.
Okay, it's an open question. I have not the solution.
I don't have a solution here. I don't know. I need to think about it more. It's true that there is this problem of prior knowledge that would be nice with. But no, I don't have the answer right now.
Okay, no worries about that. It's a really open question. I just write down some question while I was reading your thesis, and this question came up to me. And well, still in the closed loop chapter. So when you go a little bit further concerning the example session, the numerical example section. So you give some interesting example, which greatly helps our understanding. So you come up with Monte Carlo simulation with 1,000 experiments, if I will remember. Okay, this page. Okay. So you give here the result of the mean of all the 1,000 experiments. Okay. And what about the dispersion around this result? I mean, what about the standard deviation? Okay, I know that you don't focus on this, but just for us to have an idea of is it always focusing on this point, okay, or not?
Well, I didn't. I verified it also on of a few Monte Carlo simulation where I could verify parameter vector by parameter vector, and it was close to what I could have done here, but I didn't do is I could estimate the uncertainties that we have in this case because I know the true system. So I could do the calculate the covariance matrix and then calculate the uncertainty ellipsoid for one for a given probability. Yes, it's true that I could have done this. Here we want it to be quite simple, and actually it's what we have done in the article. So I just passed. But yes, it's interesting to do this, to calculate this in order to see if there is not a point that corresponds to the fact that I don't have. The problem is verifying that you have the data informativity is more complex than verifying that you don't have it. Because when you don't have it, it will point to things that you don't have. But when verifying that you have it, you should do it, I think, with this uncertainty analysis.
Yeah, for sure. And what would be your, since you have been working on it for several days or weeks, I don't know, maybe you have a nice expertise now, and if you have to estimate such a system like the one you provided in your thesis, would you prefer to choose, which kind of input signal would you prefer to choose? Because you have given two different, but what would be your advice?
Well, so it depends on the limitation of the experiment design. If you are free to do things, it's your first identification, consider filtered white noise excitation with a positive spectrum density. You don't have a problem with the data informativity. It depends actually on the situation that you have for the experiment limitation. If you are free to do this, I suggest to do this. It's the same thing for the multi-sign with what we talked earlier with Johan, that if you parameterize independently your input, it's better. But for the experiment, it may need a longer experiment. Depends on, I think, I will go for something that is easy for the data informativity. However, if it's your second identification, you have some prior knowledge, you have the first identified parameter, then in this case, it's better to do an experiment design, a least costly experiment design thing with a very real accuracy constraint to satisfy and something like this. But if it's your first try, well, it's better to use something that is easy for the data informativity.
Okay, nice. So then let's move to the last chapter, because what I really appreciate in your thesis is that you have strongly theoretical results, but also a really nice application, and we can see that you can handle both. So it's a nice point. So I'm not sure to have really well understand a particular point. So concerning the last part of this chapter, you choose a gray box identification strategy.
Yes.
Well, if I understand, so you aimed at getting a simplest model from the data simulated from this accurate, well, let's say accurate the gray box model. Am I correct?
Yes.
Okay. So you perform an identification from data reconstructed from a previous model.
Exactly.
Since you previously say that sometimes you can get some extra dynamics which are quite difficult to handle with gray box model, don't you think that this kind of strategy is maybe sometimes, let's say, dangerous? Because if well, you can estimate only what it is in the data. So if the data coming from the gray box model hide some things, then you will not be able to get an estimation of it, even in the simplest model.
Well, I will answer that. The model that I obtained satisfied the full order some residual test that I've made. So it should not have done. It should not have. No, sorry. There should not be another extra dynamics, but of course you can have some dynamics which can be hidden during the test. So supposedly our black box model is complete. So we do not have this problem of extra dynamics. However, we can have another problem that it's not the true system that we have identified. It's a true system with some uncertainties, and these uncertainties may have an impact when you are going to generate the data. If I'm clear about, and so you may have a dangerous thing that might happen because of these uncertainties. But for the extra dynamics, normally it's verified by the full order assumption, full residual test. So it's complete, but with this uncertainties thing. But since we try to keep them small, it might be dangerous. Yes, you're absolutely right.
Okay. Well, a more general question. So, so I understand your point answering the question from Okan about the full order, but another question quite connected to this. All the results derived in your thesis assume that you have an infinite number of data available. Okay, fair enough. But do you have an idea of, well, let's say, how to extend this work if only a limited number of data points are available? I mean, with infinite and not infinite.
So how to see, how to study the data informativity in this case for this finite number of data, something like this?
Yeah.
I know that there has been some work on this to verify that you have this kind of consistency with the finite number of data. And I know that it can be quite hard to verify it. But to extend it, yeah, I don't know, because it's the same thing with Johan, is this transient time, for instance, I think it's
connected
to rich information. So it might be a good idea, but I don't know how we can extend it. I think that you have to take your signal in my analysis, but not considering the E-bar operator, but I don't know.
Yep,
but
definitely.
I think so. And in this case, well, I think that, yeah, it may be possible, but I'm not sure. I don't know.
Okay. Some work have been already done on this.
Yeah, I know about this.
Kind, so maybe we can have a look at it. Yeah. Okay, and let's end up with a more philosophical question. I mean, so a little bit like Johan, if you have a postdoc, a 3-year postdoc, or even less, 1 or 2 years postdoc, you have given several open issues, open discussions in the last part of your chapter. Which one would you like to choose to develop? Which one would you prefer? Which one would you like to see for 1 year, or I don't know, to work on it? Which one is a more interesting things to do? I mean,
so
for you,
if I don't consider the advice that people gave me after my presentation on data informativity, I would say that indeed try to change this rank computation problem that we may have can be inaccurate. And the second thing is this set here for the parameter that this geometrical study of this this set in order to conclude. But now, if I consider the advice that I already get, is that, well, the data informativity is indeed a good property, but what we want in reality is to do an experiment design, have some accuracy constraints validated. Yep. So if I would have to take the advice, I would go for an experiment design more for future works. But indeed, if I could work again on the data informativity, I would say, yeah, this thing is really for me something that I want to know. How can I handle this problem of rank and this problem of geometrical set to do?
Yeah. Okay. Thank you for this interesting discussion.
Thank you.
Well, let me now give the floor to your supervisor. I think maybe we can start with the youngest, so with Laurent.
Hello, can you hear me?
Yeah. Yep.
Yes.
Okay. I would like to thank everybody, the members of the jury of Kévin. Thank you, Marion. Thank you, Okan. Thank you, Juan and Guillaume, for accepting to evaluate the work of Kévin. It's a pity that we could not have you physically in Lyon, but I think through the internet you are very present. Huh? Very good questions, very good discussions, and thank you for your time, and thank you for your expertise. I would like now to thank Kévin, congratulations for the presentation.
It
was very clear, very nice. I really appreciate it. I thank also, I would like to thank the founding source of this thesis, the project Next for MEMS. Thank you, Anton, for being here. I hope that you can hear me. Thank you for making this possible. And thank you, Xavier, for associating me with this thesis, this nice work. This was really a very pleasant adventure. Because Kévin is an outstanding student, very motivated, rigorous, hardworking, and it was really, really nice to work with you, Kévin, during these 3 years.
It was the same pleasure.
At the end of the journey. And I'm really happy that you will continue the research in a postdoc in the KTH.
Yes.
Gain more experience to strengthen your research capacity. I think you are already a very mature researcher, very, I'll say it, you're very professional and very motivated. I think that if you continue like this, you will have a really great career as a researcher. So I really encourage you to continue this way. So there are still many works to do. There are still many perspectives associated with this work. I mean, judging from the numerous questions raised by the members of your jury, I think many avenues for still digging up in these interesting topics. So I don't have questions. I think it's not the right time for me to ask questions. But I appreciate really all the questions that have been raised by the members of the jury. Thank you really for opening the scope of this thesis through your questions. So I will not be that long. So I will leave the floor to Xavier, who work more closely with you. I was a co-advisor, but I was a bit more distant than Xavier, who really follows the matter closely. Thank you, Xavier, for a nice work. And thank you again, Kévin.
Thank you, Laurent. It was very nice to work with you.
Okay, thank you, Laurent. Xavier?
Thank you, Laurent, also for this nice collaboration. I will start with that. But what can I say more? Everything has been said, I think. Laurent has already thanked the committee members. I want to abound with that. Johan, Guillaume, Marion, and Okan, really thank you for the time you have taken to evaluate this work. And also for the interesting questions, inputs, and new ideas. We have still things to do. It's really appreciated, folks. Also I want to thank Kévin for the nice collaboration during these 3 years. I use the word collaboration because I've never seen you as a student or a PhD student, more as a collaborator, as a colleague. And so it has been a pleasure to work with you. And I can only praise your professionalism and your enthusiasm. Everybody has seen it. Your enthusiasm is outstanding, I would say. And I've also been impressed by your ability to work autonomously, and that's very important for a researcher. And also by your team spirit in this big project, regrouping 4 students, a lot of academics, a lot of industrial partners. And so also, as Laurent mentions, I want to thank Anton, who with his enthusiasm has started this project, and Gerard and I helped him a little bit to build it. And also I want to thank all the other members of this project, Ampère, Fabricio, Federico, and Jorge. Eva also joined for a while, and many others from the industry. people with whom Kévin, Laurent, and I have cooperated, and nothing would have been possible without them. So thank you very much. And I think everybody, all these people are listening via the YouTube streaming. And it was really nice working with you folks. And I've also think, and everybody has said it, all the committee members, that this industrial project has given a very nice flavor to the work of Kévin. And so that's, wow, that was all. And I give the floor once again to Marion.
Okay. Okay, I'm arriving. Okay, it works. Okay, thanks. So I think it's now time to end this part of the thesis or the presentation. So I suggest that the committee member can meet only themselves, I mean.
Yeah, so I'm going to make you animator.
Ah, okay.
So now you're not.
Well, that's the more tricky instance. How to do that? Okay.
And Fabricio, you can